on sequential circuit testing. As we discussed in the last class, that in order to test any circuit, we need to go through these three things. One is the fault that may potentially occur in the circuit has to be sensitized. So sensitization simply mean that at the fault site we should have opposite value of the faulty value. Then that fault effect, that means the uh, fault free value and faulty value, those are distinguishable. That has to be propagated to one of the primary outputs so that we can observe. We cannot observe anything in the internal nets. And then in order to propagate this, you need to set the off inputs of the gates which are falling on the path to the primary output to the non-controlling value, and that you can do by applying some inputs. So you have to trace back to the primary input, and then you that we call as the line justification. So these are the three say main key points in development of any say test generation algorithm. And the many algorithms that you have already discussed, like a D algorithm, PODEM algorithm, fan, Socrates, spirits, and then there are many more algorithms which are using learning from the circuit. Learning from the circuit means, like here, if I can assign value, say A as 1, in that case you know that D can never ever be 1. D has to be 0. So that kind of learning you should have from the circuit, and that learning can be used in repetitive generation of the test for the different faults. So now there are, I mean, many algorithms which started to use the learning. Uh, so this ATPG algorithm works well if I have a combinational circuit wherein you have some input and then one of the output. Now, when we go for the sequential circuit, in the last class, we discussed that sequential circuit is basically defined by a tuple, which says that here the circuit has a set of states S, and S0 is the initial state. There are input symbols that it can consume. There is the output it produces, and then there are two functions. One is the transition function, another one is the output function. Now the transition function is from state and input to the state, and lambda, that is the output function that goes from either state and input to the output, or state to the output. Based on this is a called as Milli machine or Moore machine that we discussed yesterday. Now, in order to design this machine, I need to have some storage element, and that storage element, and then two combinational logic. One logic that provide me the delta, another is which provide me lambda function. And this delta is dependent on the value of the state as well as the primary input. So this is primary input, and then this will modify the value in the storage, and the lambda will also dependent on either primary, either the current value of state, and then it will give me the primary output. And this may dependent on the primary input as well. So if I look at the external interface, in that case this is my external interface wherein I have input and output. The input we call as primary input, output we call as primary output, and we are calling this primary because one can observe here. However, this output which goes to the storage element we call as pseudo primary output, and the value which is available at the storage element, and that can be supplied to the combinational logic block, that is lambda or delta, we call as pseudo primary input. Now if there is a fault at some say in, say, I mean, here I have shown that delta and lambda both are two different functions. However, lot of logic they share, and therefore whenever you are optimizing the entire circuitry, in that case you will get a optimized circuit as storage and one combinational block that has function delta and function lambda. So this will go here, this goes to the primary output, primary input is coming from here, and the value from the storage will come over here, because some of the logical functions are common between lambda and delta, and therefore we don't need to implement them again and again, and therefore this is combined. Now let's say that here I have a function. So I have a fault here. This fault f, say this f stuck at fault. This may be stuck to logic 0 or logic 1. What I need, I have to first sensitize this fault. What I want to do for sensitization, I want to sensitize this by using only the primary input as far as possible. But sometimes it is possible, sometimes it needs the help from the storage element, and if it needs help from the storage element, in that case I also need it from here, and I don't know what is the stored in the storage element, so that I have to assume x. If I assume x, perhaps this may or may not excite the fault. If this may not excite the fault, in that case I have to go back and replicate this logic. So this is a combinational equivalent, is this is a combinational block, and if I can directly excite it from the PI, we are good. If I don't this we say PI pseudo primary input and pseudo primary output. If I don't need anything from PPI 0, sorry, X, in that case it is great. If I need something from this one, in that case I have to replicate this combinational logic block once again, and so that I'm getting this PPI, and then this is but there is a fault over here, and then the same fault would be there in this this copy of the circuit. Keep in mind that when I'm saying that we are making a copy, it doesn't mean that we are making a copy on the chip. On chip there is only one copy. However, for the test generation point of view, in software we are making the additional copy, and you keep on doing this, like here, say here this is mm, say that this is coming from here, but now if I need this only from this primary input, and you need x from here, in that case you can stop. Now my fault effect, this can from here the fault effect can go to the primary output, or this can go to the pseudo primary output. If it goes to the primary output, in that case I'm fine, I can stop over there. However, if it is not going to the primary output, in that case, I have to further say make a copy of this with the same fault, and then have to transfer this pseudo primary output, which is coming from this logical block, as pseudo primary input to the next block, and then if I can, I'm able to propagate this to the primary output, in that case you are done. So that means you have to keep on making a copy in the backward direction for the line justification, and in the forward direction for the fault propagation. So this is the time frame when I'm exciting the fault. So fault excitation happen during this time. The forward direction, we are making a copy for the fault propagation, and backward direction we are making a copy for the fault for the line justification. And we have to go all the way until we need or we demand x from the pseudo primary input in the backward direction, and we keep on going in the forward direction till the point wherein our fault effect reaches to the primary output. So this is how we manage to obtain the test vector for a given fault. So here then I need one additional step that is called that we called yesterday as initialization, initializing the circuit to the non-state. So that means here with this line justification time frame expansion, I am coming to this point wherein I can initialize in some state, and after that I can generate the test vector from that particular state to excite that particular fault, and then now fault effect can reach to the primary out. Either it should reaches to the primary output or it reaches to the pseudo primary output. If it reaches to the primary output, we can stop. If it reaches to the pseudo primary output, in that case again we have to say enroll that. So here you need one additional step, that is initializing the circuit to a non-state. So in last class we were discussing that any synchronous sequential circuit we has a few flip-flops. Now the circuit can be of two types. Either one is there may not be any cycle in the circuit, so that means here only it is the feed forward circuit with some storage element. For example, if you look at the pipelining in a microprocessor, in that case you are feeding from the input, and then it has to go through various pipeline stages and then reaches to the primary output. Like it has to go through from the phase to decode to execute to memory to write back. So that is the only feed forward. So those kind of circuits we are cycle free circuit. Now in cycle free circuit there is no feedback, and if there is no feedback, in that case the number of times I need to replicate my circuit for the test generation is equal to the sequential depth plus 1. Sequential depth is defined as the maximum number of flip-flops we encounter between any pair of input and output. So let's say that here if there is a pipeline circuit wherein, so you have in pipeline circuit you combination logic, there is a register, another combination logic, there is a register, another combination logic, like this. So now here in between in this circuit, if I look at that from any primary input, this is my pi, and then here this will go to the po. In that case we are passing through the two registers, and that means here two flip-flops. Any path will pass through the two flip-flops. In that case we define as a sequential depth as 2, and therefore we have to expand this to at least three time frames to generate the test vectors. So so now here I know the sequential depth, and based on the sequential depth we can decide that how in worst case, this is like the worst case, not the best case. You don't need to go beyond this. So that means there you can decide, if you are not able to generate the test vector by replicating the sequential depth plus 1, that means that fault is not testable fault. Now this will bring a new scenario in the test generation, that there are some faults which may be combinationally testable. I believe you people have already learned that the some of the faults which are not testable fault. Uh, So some of the faults which are not testable fault, like here, for example, if I have NAND gate, and in this NAND gate, this is the structure of the NAND gate, and if I say that this at this branch, my fault is stuck at 1. If fault is stuck at 1, in that case, this is A, this is B, so I need to excite this fault. I need opposite value, that is 0. But this opposite value will also propagate to the another input of this, and this another input, when it becomes 0, output will always be equal to 1, and I cannot propagate this fault effect here. And therefore this particular fault doesn't have a test vector, and we call that as a redundant fault. So redundant fault are the faults which whose presence doesn't upset the circuit or doesn't lead circuit to malfunction. So in this case, even if this fault is there, if this fault is there, that means here my circuit will become what? This is equal to 1, always 1, and then now this I am giving this A, and then this is output B. So this output B always would be equal to A bar, and hence if even if this particular net is permanently say stuck to logic 1, even in this case the circuit will work correctly as we desire. That is coming because of the redundancy in the circuit, because essentially this circuit is what? This is an inverter. It has one input and one output. So inverter you can implement using 2 transistors. Now NAND gate I am implementing using 4 transistors. So then there is a redundancy in the circuit. So the redundant faults are the faults who are not testable, or for which there is no test vector, because they don't lead to the say malfunctioning of the circuit. So now we define 2 terminologies. You must have I mean, these terminologies might have already been discussed. One we call as the fault coverage. Fault coverage is defined as number of testable fault. Number of testable fault means here the faults for whom we have test vectors available to test, divided by the total number of faults. Right. So like here, let's say that here I have 1,000 faults in my circuit, and I get the test vector for 950 faults, but I don't have test vector for say 10 fault I mean 50 faults. In that case, this is my fault coverage would be 950 divided by 1,000 multiplied by 100, that is 95%. However, if the remaining all 50 faults, if they are untestable, or they are redundant faults, so that means there is no test vector. If I can say that there is no test vector corresponding to them, in that case we call them as a redundant fault, because I cannot generate the test vector for them, and therefore now it's really not wise to say that this particular say circuit has lower testability, as in this case it is showing that here 95% faults are testable, 5% are not testable. I don't know what will happen if those faults happen to be there in the circuit. But I know that if these 50 fault 50 faults are redundant faults, then they are not going to create any say problem in the circuit operation. And then we define another term that we call as fault efficiency. Fault efficiency is defined as number of testable faults divided by total faults minus number of redundant faults. So that means this become 950 divided by 1000 minus 50 multiplied by 100, and that comes out to be 100%. So actually we are looking for the fault efficiency as 100%. So we have to generate the test vector such that my fault efficiency can be or should be 100%. Sometimes this fault efficiency is also referred as test test coverage, but then test coverage is a very vague word that is sometimes used for the fault coverage and sometimes used for the fault efficiency. So if you see the test coverage, then please be careful that you have to make sure that what this refers to. Now, maybe then one can say that here fault efficiency is the only metric which is useful. Why I use the fault coverage? There is no meaning of using these two metric to assess that how good your test vector set is. Now, and you can see that here the difference between the fault coverage and fault efficiency is coming from the redundancy only. So this for the difference between fault, we evaluate these two metric, and difference between the fault coverage and fault efficiency tells you that how much redundancy you have in the circuit. Now, so this assess the redundancy in the circuit. Now you can say that, let's say that here I found out that there is a 5% redundancy in my circuit. Maybe you the test engineer can find out that and then can report to the design engineers. If design engineers are fine with that redundancy, it is fine. Otherwise, so like if you say 5%, they may say that yeah, it's okay. We are fine with that. If you say that the redundancy is 30%, in that case perhaps they may need to rethink about it and then may need to resynthesize the circuit. Redundancy sometimes comes unknowingly, sometimes you introduce knowingly because of say ease of manufacturing or something. Like for example, if I want to design a 8-bit adder, then in 8-bit adder actually let's say that if we want to implement ripple carry adder, in that case you need 7 full adder and 1 half adder. Now, however, mostly we are developing the 8-bit adder as 8 full adders, because then I can make a cell for one full adder and then can replicate. VLSI likes to have regularity, and this provides the regularity. And because one of the half adder is unnecessarily we are using, and that brings in the redundancy. So redundancy may come because say knowingly or deliberately. In this case, we know that there is a redundancy in the circuit, but that makes my effort less. It can make the layout more structured, where it needs less effort to lay out the chip. Otherwise, I need to design two circuits and then have make the layout of those two circuits. So or sometimes redundancy comes when you want to optimize your circuit for the performance over the area. So in that case you may need to do some task redundantly in order to compute that faster. So this, I mean, in nutshell, this difference between the fault coverage and fault efficiency bring in the redundancy. Now, if there is a redundant fault, in that case, that is the most difficult part in the test generation, because you don't know when I should call that fault as a redundant fault. In worst case, you may need to exhaustively explore all the possibilities of the test vectors before declaring a fault as a redundant fault. If you are using Boolean difference kind of method, in that case the complexity or amount of effort remains same whether the fault is a redundant fault or fault has the test vector. However, if you are using the other algorithmic method like D algorithm or PODEM or FAN or any other ATPG method, in that case the the amount of work you may need to do to generate the test for a fault which has test vector, and amount of work you need to do for to identify a fault as a redundant fault is very different. Generally, as I said in yesterday's lecture, that if a fault is a testable fault, in that case there are multiple vectors which can test that particular fault, and out of so many test vectors, you are likely to find at least one of the vectors quite fast, and therefore there is a significant difference. Now if you are not able to say find a test in within some time, in that case we have to declare that, I mean, we have to abort the generation of the test for that particular fault. And if you abort, in that case, so now I say that let's say that here I'm aborting for some faults. Let's say that here 20 faults I abort out of 100 faults. uh, I had total 1000 fault, 950 I have test vectors. So these are testable or detectable, and these are the aborted, and then rest of the 30 faults are redundant. Now redundant faults are 30. So now my fault coverage will go as the 950 are detectable fault, and then divided by total fault multiplied by 100. My fault efficiency will become this 950 I have test vector divided by 1000 minus 4, I mean 30 faults are redundant faults, and multiplied by 100, that is 950 by 980 into 100%. Right, so now my fault efficiency is less than 100%, and these 20 faults which I have aborted are under the assumption that these faults might be the testable, might be the redundant fault, but we have no idea whether they are a redundant fault or not. If these faults are not there in the chip, then we are not losing anything, it's perfectly fine. But if this fault happens to be there in the chip and this happens to be a testable fault, in that case we don't have test vector, and then that fault will go or will escape. That we refer as test escape, and because of that maybe at some point in time it will be caught. So now I have say in combinational logic we have some faults which are testable, some faults which are redundant, and some faults which we abort. We are aborting because the I'm not putting enough effort to say generate the test or declare that fault as a say uh, redundant fault. Now redundancy is one thing. Now, this is a combinationally redundant fault. If I declare that there is no test vector exist for this particular fault, like in this case for this stacked fault, there is no test vector exist, and I can declare that as a redundant fault. Now, these are combinationally redundant. That means my combinational ATPG that uses either Boolean difference or any algorithmic method like a D algorithm, PODEM, FAN, etc., etc. However, this may possible that the fault is combinationally testable. However, the fault perhaps may be may not be able to propagate the fault effect to the primary output. And those faults are though they are combinationally testable, but they are sequentially redundant, because sequentially, even if those faults do exist, they will never be able to propagate the fault effect to the primary output. So in that case, under the presence of those faults, your output will never ever be affected, and those faults we call as sequentially redundant faults. Identifying the sequential redundant fault is much more tough exercise than the combinationally redundant faults. Now, the faults which have the combinational test vector, but then sequentially, to find out whether this is sequentially redundant, what I need, okay, let's go here. I need to say say in combinational circuit, at the most I mean, we need to explore all possibilities at the primary input. Now here I have to I mean, more than that, I have to say unroll my circuit n number of times. Now, what should be the value of n? Wherein I can say that here this is enough, I don't need to unroll more than that. And if I cannot generate the test vector within this one, in that case, I can call that fault as a sequentially redundant fault. Now that task is easy if it is a acyclic or cycle free sequential synchronous circuit, because at the most I may need to unroll that circuit or replicate that circuit equal to the sequential depth plus 1. So if sequential depth is 2, in that case at the most I need to say unroll the circuit or make a copy of that circuit 3 times. And if I cannot find the test vector within 3 times, in that case I can say that that particular fault is a redundant fault and we don't need to worry about that. So this can work reasonably well. The bigger issue is that so if I have a um so now when I say unroll the circuit like this 5 times, this is combinational logic, combinational logic, combinational logic, combinational logic, combinational logic. Here I apply primary input, all primary inputs give me the primary output, primary output, primary input, primary output. This is primary input, primary output, and this value from the pseudo primary input, this is PPI, should start from X, and it has to go to the next time frame, next time frame, next time frame, and the output here I ignore that. Here I am doing the default sensitization. These are for line justification, so that means line justification, or we call this as initialization, and this is for fault propagation. Now if I look at the circuit, let's say that here this circuit has 1 billion gate. I replicate this 5 times, so this will be 1 billion, 1 billion, 1 billion, 1 billion. Now my total circuit size will become 5 into 1 billion, so that means here 5 billion. Assume that one circuit has 100 primary inputs and say 50 primary outputs. Now my total unrolled circuit will have primary input, that is 5 into 100, so that means 500 primary inputs, wherein you need to find out the value of those primary, those will act as a primary input. So this will act like a large combinational circuit with 5 times the number of gates. Then it has the 5 times the number of primary inputs, and number of primary output is 5 into 50, that is 250. So the circuit will become large in size. It will have many more number of primary inputs, and if the number of primary inputs will expand, in that case the number of possibility will expand, and then the time it will take to generate the test will say increase. And the, as I said, the biggest problem is when you say, so a fault has to be replicated in every combinational logic. So that means here you have 5 faults, not a single fault in this circuit. And now if I consider this entire circuit as a combinational circuit and generate the test vector for this, let's say that here this is the entire combinational logic I can consider, with 500 inputs, 250 outputs, and say 5 billion gates. So you can see the complexity of test generation will increase manyfold. That is still doable if the number of times you may need to unroll is limited. However, if my circuit is a cyclic circuit, that means there are cycles in the circuit. If it is cyclic circuit, in that case you may need to uh, you may need to say unroll the circuit to 9 raised to the power number of flip-flops times. 9 is coming here because we cannot, yesterday we have discussed that we cannot use 5 valued logic, we have to use 9 valued logic. So that means you may need to explore all possibilities, all 9 possibilities. And in order to do that, here I may need to explore this. So total 9 possibilities in every flip flop, and then there are n number of flip flops. In that case, this 9 raised to the power n, and this is a humongous number, right? Even if you have very small number of flip flops, it can, I mean, it you can easily have very large number of outputs, and that is needed when I want to make sure that my fault is a sequentially redundant fault or not. If fault is not if fault is sequentially redundant, in that case we can drop the test generation for that. Now when I say that here my fault is a sequentially redundant, in terms of the cycle free circuit, it is bit easy because I know the maximum bound is not that large. Here the maximum bound is very large, like as we discussed yesterday as well, that even if you have 2 flip-flops, in that case you may need to unroll this circuit 81 times. So when I unroll this 81 times and you are not able to generate the test for that particular fault, in that case you can say that here this fault is a sequentially redundant fault. That's the biggest issue that we are getting. Moreover, now you also have to look at that when I mean, in worst case, to declare the fault as a say redundant fault, I may need to explore all possible combination of that, and all possible combination means here at the I mean, primary input. Now I have 500 primary output, and these 500. So you may need to explore all 2 raised to the power 500 possibilities in worst case. So worst case is too bad if you are using a sequential circuit. So this makes the sequential circuit test generation a much more say difficult exercise. So cycle-free circuit here is characterized by absence of cycles among the flip-flops. So there is no cycle. There is a feed-forward path from primary input to the primary output always, and that defines the sequential depth. So sequential depth is the maximum number of flip-flops on any path between a pair of primary input and primary output. Both good and faulty circuits are initializable. So that means here if it is a cyclic circuit. In that case, you can always initialize that circuit. Initialize that circuit means here I can always make sure that by this time here my circuit or my primary in pseudo primary input will come to a point wherein I can say safely say that here it will be in this particular state. So if it is say cycle free, in that case it is initializable. Test sequence length for a fault free circuit is for a fault is bounded by sequential depth plus 1. That's what we have discussed. Let's say that we take this one example with three flip flops, and you can see that there are two inputs to the circuit. This is one input, and then the second input, and there is one output to this the circuit. So this is my circuit. Now if I draw a say structural graph that we call as S graph. S graph has a flip flop as node, and if there is a path between the flip flop to another flip flop, in that case we make an edge. That is called as structural graph or S graph. Now in this S graph there will not there should not be a loop that defines the whether circuit is a cyclic circuit or a cyclic circuit. Now this is flip flop F1, so this will have one node. Flip flop F2 will have another node, and there is a path between the flip flop F1 and F2, and thereby we will have an edge between F1 and F2. F2 and F3 also there would be an edge, because the path the path exists between F1 and F2, and hence I draw an edge between them. There is a path from the say flip flop F1 to flip flop F3, and therefore there would be edge between flip flop F1 and F3. And now there is no say cycle in this is cycle free, and hence we call the this fault as a say um, what we call cycle free circuit. Now let's say that I make an equivalent circuit of this by I mean equivalent combinational circuit. Equivalent combinational circuit will have three gates, I mean four gates. This OR gate, uh, OR gate, then inverter, NAND gate, and or another three input OR gate. Now this circuit will become like this. As you look at this, this is my circuit, right? Wherein the three inputs are coming from F1, F2, F3, and then there is one input A, and another input is B. So this is, let's say that here input A, this is input B. So now these are the input A and B, and I replicate this couple of times. Now how many times I may need to say replicate this? I may need to replicate this the maximum say number of flip flops between this input so B and output. Let's say that output is Z. In that case, between B and Z there exists a path from B to flip flop 1 to flip flop 2 to flip flop 3, and then output Z. So there are three flip flops in between. and therefore my sequential depth of the circuit is equal to 3, and hence in maximum we may need to replicate the circuit 4 times. And I have, let's say that I replicated this 4 times, and then see that here whether the whether I mean fault that exist at the input of this two input OR gate is we can test or not. So this is the fault site that I have. I want to test. The fault is here. At this point, if there is a fault, stuck at zero fault, in that case whether I can test that particular fault or not. Now in this one, what my aim is to always propagate the fault effect to the primary output. So now if I there is a fault over here, then I have to create value that is just opposite to the faulty value is 0, so therefore I demand 1 from here. If I demand 1 from here, in that case I can directly demand 1 from the primary input A, and that I can assign as 1. But in order to propagate this fault effect to to the output of this gate, I need another input of this say or gate to the non-controlling value, and non-controlling value is 0, and thereby I go back and then I demand this value 0 from the flip-flop 1, that is pseudo primary input. If this pseudo primary input is 0, so that means here I am demanding something from the pseudo primary input, and therefore it has to be replicated one more time in the backward direction. I will come back to the backward direction in a minute. Then let's try to propagate the fault. So now my fault effect is at the flip flop f2. So that means here it is not able to propagate to the primary output. It is propagating to the pseudo primary output f2. F2 is the flip flop 2. Now from the flip flop 2, so here my fault effect is over here. हाँ, दिख नहीं रहा है. So now here my I had a D. This D will appear here as D, and so now my fault effect is at the input of this gate, NAND gate. Now to propagate this through the NAND gate, now fault effect has to be propagated from the through this NAND gate. What I want the another input of the NAND gate equal to the non-controlling value, and non-controlling value of NAND gate is 1, and thereby I can justify that 1 value 1 from the primary input of the previous time frame. So I will go here and assign value 1 over here, so I can assign through this one. Still my fault effect is at the output of the NAND gate. Now, in order to propagate this output from the NAND gate, what happens is, so there are two things which happens. In the previous time frame that we call as time frame 0, wherein we are sensitizing the fault, the this input we demand 0 from the flip flop or pseudo primary input. But the moment you assign 0 here, in that case the output of this NAND gate will become 1, and this 1 will propagate here. When 1 will propagate here, in that case always one of the input of this AND gate is 1. That means here this will decide the output of this OR gate, right? If this value is 1, in that case output would be always decided by this, and this fault effect will disappear from here, and therefore I cannot move this fault effect to the primary output. But then there is a possibility that there is another fan out branch from this point that can take me to the pseudo primary output, that is f3. So when it goes to the pseudo primary output f3, here I am getting this fault effect. that is say d bar, because this d will come here as d bar, and then that d bar will propagate over here. And now to the one of the input is d bar. If I can make another two input as the non-controlling value, so that means 0 and 0, this one of this value 0, I can simply justify by by line justifying to this, and this can go back to this a. I can make this as 1, and hence I can justify this 0. Another value 0, I can justify this by having 0. I can have only when I have both of the input to this NAND gate as 1 1. Now this one can easily justified by justifying value 1 over here. This one can be again justified through having value 1 over here. So in this case, now I can be able to propagate to the primary output. However, still one task is left, and that task is I am demanding this value 0 from here. Now for that again I have to replicate. I mean I have replication one time in backward direction, and if I demand 0 from here, in that case that is connected to the primary input of the previous time frame, and then I can go back over here and will assign 0. So that means in this case I need to have my test vector would be need four vectors. One is a is x in the first time frame, b is 0. Then a is 1 and b is also 1. Then a is 1 and b is 1. Then fourth time frame a is 1 and b is x. And then at the output here we are observing whether it's a d bar or not. D bar means here it should be fault free is 0, faulty is 1. So if I can obtain this one in the after four time frames, so I apply four inputs, and then at the end of the fourth cycle I can check what output I am getting. If output is equal to 0, in that case I will say that my circuit is fault free. Output is equal to 1, in that case I will say that here my circuit is faulty. This is how we generate the test vector for a given fault. I hope I try to make it clear that how you can unroll the circuit and can generate the test vector. For cycle free, as I said that here it is say we need to unroll this limited time, and
Like, sir,
therefore we can try. Yes.
some questions. There are some questions in the chat box.
Yeah. Sure.
So Sai Kumar is asking, what is the abort faults?
The abort faults are like here, for example, I said that earlier as well, that say that I have a circuit and generate the test for that. Now let's say that here it is one, I target one particular fault and start to run my ATPG. And let's say that here it is to generate the test for one particular fault, it takes 5 days, right? Because in worst case, to generate the test, it may need to explore all possibilities that can occur at the primary input. All possibilities are 2 raised to the power n, and if I say circuit with 100 input, in that case 2 raised to the power 100, that will consume something like here say several centuries, right? So I may not be able to explore all possibilities, and in worst case I may need to explore, I may go through a path, because in some cases there is no test, and until unless I exhaust all the possibilities, I may not be declare that fault is a redundant fault or not. Or maybe after that exploring all possibilities, there may be only one test vector, and that I may get after exploring all possibilities. So then what do I do is I put the limit on the time, that oh, if say for one, say for other all other, say I have thousand say thousand faults, 950 faults I got test vector quickly, let's say that in 1 hour. But then for 950th fault, for one fault it is taking 5 days. Now it is the question, should I keep running for this particular fault and let it decide whether there is a test vector or there is no test vector for this? And that may take any amount of time. I have no idea how much time it will take, because in worst case it can take 2 raised to the power the number of inputs, and that number is a humongous number. So what do we do is, after a while we put the limit on time, that if this much time is expired, you say that here perhaps there is no test vector for this particular fault, this might be the redundant fault, and therefore abort the generation of the test for this particular fault. And so now this is, say, my F950 first fault, and now I don't know actually about this fault, whether this I mean there is a test vector for this fault or not. If there is no test vector, there it may possible that there is no test vector, so that means here it is a redundant fault. If it is a redundant fault, then it's a great. If it is not redundant fault, and if that fault doesn't exist in the circuit, again it is great. But if that fault exists in the circuit and it is a testable fault, then I don't have test vector for that, and that fault will go unnoticed, and that will increase the defect level of the circuit, because we are shipping that chip as a good chip, and when it is operating in the circuit, somebody will detect that particular fault and then will send back the entire system to me. So we need to abort because we cannot exercise all possible inputs. Is that clear? How we identify fault is redundant fault. So as I said, sometimes it is bit easier. Like for example, in this example of this NAND gate, I get this that see, at the same time you need to excite that particular fault, so that means that fault must be activated and it has to be propagated to the primary output. Now in this case, the same fault may not be excited and propagated to the primary output at the same time. There is a conflict, and I can quickly understand that this fault is untestable fault, because this excited, for excitation I need value 0 at the input. If I have value 0 at the input, in that case that will block the propagation to the primary output, and hence both possibilities are not there at the same time, and hence there is no test vector for this. It is easy to generate or to identify fault as a redundant fault if you are using Boolean difference method, but Boolean difference method is much more tougher to implement. Doing Boolean computation is not that easy job. So but in this case it is easy. In other cases, perhaps I add the primary input, but you might have I mean, learned the, say, the simplest example I use, PODEM. The D algorithm is much more difficult and it will take much more time. But in D algorithm, I mean, in PODEM algorithm, we go back all the way to the primary input. And now in to declare the fault is a redundant fault, in worst case I may need to explore all possibilities at the primary input. I have to build the entire computation tree at the primary input. Like if there are three inputs, in that case I'm, until unless I say explore all possibilities, eight possibilities at the primary input, I cannot say that a fault is a redundant fault or not. So that's where we find it difficult. And as I said, that the in worst case the test generation complexity is an test generation problem is an NP complete problem. So that means you cannot generate in polynomial time if you go deterministically. However, the most of the algorithms which are based on some heuristics work reasonably well because there are multiple test vectors for a given fault. And when you start to generate in that case, you are likely to generate one of the test vectors out of many test vectors very quickly. And that's how the test generation became the practical problem, and we are able to do that. But then obviously we need to abort sometimes, and then when we need to abort, I don't know that what would be the what I mean what will happen if those faults may come. If they those faults appear in the chip, in that case there is no way to detect that. So that's the problem, and that thing is reflected in fault efficiency. Ideally, fault efficiency should be 100%. If it is not 100%, in that case, you have that much lower confidence in your test set. Did I did I answer your question?
Yes, sir. Thank you, sir. Sir,
So,
do you need some break for 5-10 minutes?
okay, let's take a break for 5 minutes.
So let us be back 10:20. We will be back. We will join back. Dear participants, let's have a break of 5-6 minutes. Okay. Am I audible, sir?
Yes. Shall we start? Shall we start?
Pedro Singh, am I audible?
Hello.
Yes, sir. Can we
Yeah,
start
yeah,
with
yeah.
next? Okay, sir. Thank you, sir.
Am I audible? Am I audible?
Yes, sir. Yes, sir. Yes, sir. You are audible, sir.
Okay. So now one of the pain that we have is when I have cyclic circuit. And like if you look at any controller, those are mostly the cyclic sequential circuits. A very small number of circuits are acyclic, large number of circuits are cyclic circuits. And if it is a cyclic circuit, in that case, the maximum bound is very bad. Even for two flip-flop circuit, you may need to replicate your circuit 81 times. That's not doable. Now, even if so because all the primary inputs will increase 81 times, the number of gates will increase 81 times, number of output will increase 81 times, and then this becomes a very difficult problem. And if I happen to have, say, even 10 flip-flop, in that case, my worst case can go to 9 raised to the power 10. That is not a practically tractable problem. That is bigger pain. So now, although again I stick to my point that these are the worst case. In average case, because there are multiple test vectors, and then you don't need to go to 9 raised to the power number of flip-flop times. In much smaller number of time frame expansion, you can obtain the test vector. But in order to detect say classify a fault as a redundant fault, you may need to go to that number, and you may need to go to 9 raised to the power number of flip-flops quite often, and and it will take too long time to generate the test, and therefore there will be very frequent aborts. Like say if I'm running for a week, so in general, if you run a test program that runs for several weeks, but if one say fault start to take some days or some hours, in that case you have to abort, because there are large number of faults for which you need to generate the test vector. That makes things much more difficult. Now, so so that is the pain. So identification of sequentially redundant fault. That is one of the painful thing. One maybe just out of context, I'll tell you. Say, if I take a combinational logic and generate for the test for this, how do we do? If I have, say, there are n faults, f1, f2, fn, we generate the test vector. Let's say pick the first fault f1, generate the test vector v1, and then do the fault simulation and identify that which at all the faults are there in your circuit, which can be detected by this particular test vector, and then you drop those faults from your fault list, and then pick the next fault and then then you generate the another test vector and then do the same thing. Now this way you keep on doing, and let's say that here I generate the m number of test vectors. Once you generate these m test vectors, we do the reverse fault simulation. That I start from VM and find out that which faults are detected by this. Then I will go for VM minus 1, do the fault simulation and see that which other fault it is detecting. So I remove the faults which are detected already by VM, and then from rest if it is detecting something. If if it detect at least one of the unique fault, in that case I will retain that test vector, otherwise I drop. Then we may go to VM minus 2, and then I say that here this is not detecting any other fault other than the fault which are detected by the previous say vectors, and therefore we drop that particular test vector from my test set. This is how we do the develop the test vector set for a combinational logic. Here in the say combinational logic, the reverse test or reverse simulation is possible. However, you cannot do that reverse fault simulation for the sequential circuit, because in sequential circuit it is not a single fault, a single vector that is needed for one particular fault. You need a sequence, and therefore this particular step we cannot do with the sequential circuits. This helps us in making the test set as compact as possible. All ATPG tools are doing this. Now you look at that how difficult this exercise is. Let's say that here, so the difficulty with the sequential ATPG is circuit has poor initializability. That means it is very difficult to initialize the circuit starting from any random state to a say fixed initial state where from I can generate the test vector. So and sometimes it may take too long sequence to initialize circuit in a particular state. That is one difficulty, particularly if circuit is a cyclic sequential circuit. Circuit has poor controllability and poor observability of state variables. Now, state variables are not directly observable. You have to observe like here, if the fault effect goes to one of the state variable, in that case we try to propagate that to the primary output maybe in the next time step, but next time step perhaps it may not go to the again to the primary output, it may go again to the another state variable, and therefore the observability or controllability of the state variable is very poor. Gate count, the number of flip-flops, and the sequential depth do not explain the problem. That now mostly in combinational logic we can define the how difficult it is to generate the test vector by specifying that how many gates I have in my circuit. Although it also depends on the structure, but gate count gives you the reasonable information about the complexity of the test generation if it happens to be a combinational circuit. However, in sequential circuit, there is almost like a very poor correlationship with these parameters: gate count, how many flip-flops you have, what is the sequential depth of the circuit, or so on and so forth. Cycles are mainly responsible for complexity, as I am re-emphasizing again and again that the cyclic circuit you may need to unroll large number of times in worst case, and that's the problem. These are the two circuits for the for example, if you can look at that two circuits. One is the traffic light controller, TLC, that has 355 gates. Small circuit, number of flip-flops 21. Sequential depth of the circuit is 14, and this is the ATPG takes about 1200 seconds to generate the test, and my test coverage, fault coverage, is 89%. I can only detect 89% fault in this time. However, the same circuit, the other circuit chip, this chip A is another logic that has about 1100 gates, and number of flip-flops are much larger than this one, is 39. Sequential depth is exactly same. It needs about 270 seconds. So you can see that here circuit is a large, it has more number of flip-flops, same sequential depth. It takes much lesser number of lesser time, and gives me the higher fault coverage. So that's what I was telling, that here gate count, number of flip-flops, and sequential depth don't explain the complexity of a sequential circuit, that how complex it is, and how much time it is likely to consume when you will generate the test. This another study, this says that, let's say that the what is the difference between the cyc cyclic circuit and a cyclic circuit. Like here, there are two circuits. These are the SCAS 89 benchmark, as 1196 and as 1238, and there are two other SCAS benchmarks, which are as 1488 and 1494. The first two are cycle free, and then the next two are the cyclic circuit. The cyclic acyclic circuits have the primary input as 14. Cyclic circuit has the primary input as 8, much smaller number, right? Primary outputs are like here pretty much similar. The number of gates are almost in the same ballpark number. Now in sequential depth, of course, if sequential depth you can define for a cyclic circuit, there is no sequential depth definition for cyclic circuit, because you can keep on moving round and round in a cycle, right? So and total faults are also in the same ballpark number. However, if you look at the number, the amount of time it will spend, something like here in a cyclic circuit, it is something like a 10 or 15 seconds. However, in cyclic circuit, it is about 20,000 seconds. That is very small circuit. Say 8 inputs and about 500 gates, right? Consuming 20,000 seconds. This shows the complexity. And because of this, it's almost impossible to use the sequential ATPG to generate the test vector. Then what to do? This is one of the ways to have the time frame expansion. There are other ways. I mean, we don't have that much time to go through that, but you can use the finite state machine model directly to generate the test vector without unrolling. So now, I mean, if there is a fault, in that case, one machine transform into the another machine. So one machine, a fault in a machine M0, we can say transform into the another machine MI, where with n or fewer states. Now a test sequence is a sequence of the input that distinguishes the two machines M0 and machine MI. You can analyze, maybe this time we don't have time, but we can work out on this. So I need to find out a sequence of input that typically we are doing this kind of exercises in say verification and debugging of the state machine. So I want to find out a sequence which can distinguish these two machines, M0 and MI. So for that we define a synchronizing sequence. For a sequential machine, M is an input sequence whose application is guaranteed to leave a machine M in certain finite state. So if I apply that synchronizing sequence, in that case it guarantees me that at the end it will reach to that particular state. Guaranteed to in a final state irrespective of what initial state I have. So that means from where I started. So like I can start from any random state where in all these state elements are keeping the value x. So now I know that if the machine is good, in that case it after this sequence it is supposed to land into that particular state. And if I don't find that in that particular state, in that case I can say that this machine is not the same machine as M0. This machine is MI machine. We define a homing sequence for a machine M is input sequence whose application makes it possible to determine that final state of M by observing the corresponding output sequence of sequence that M produces. So sequence is a homing sequence. By application of those sequences, we can make sure that here or we can observe that this is in a given particular state or not. So I need to find out a distinguishing sequence that can distinguish the faulty and fault-free machine. So a distinguishing sequence is an input sequence whose application make it possible to determine the initial state of M by observing the corresponding output sequence that M produces. So I want to find out one sequence that can distinguishes that. But maybe these are the definitions I'm telling you, and this goes exactly or pretty much in the similar way as we are say verifying or debugging the state machines or uh, the sequential circuits. So as I said that sequential circuit test is a tough exercise, and sequential circuits are difficult, and the what makes it's much more difficult is cycle, and most of the circuits are cyclic circuits. And then there is no bound. A small 8 input circuit with 500 gates may take to say 20,000 seconds. You can imagine I have a circuit with million flip-flops and billion gates. How long will it take? Perhaps we may not be able to even generate the test vector for that. This was the difficulty. Even people started to face this difficulty in 80s, when the even the number of gates that you could implement on the chip were very small in number. Very small number of input and output we used to have, but still we reached to the point wherein it was almost impossible to generate the test vector in reasonable time. Now when I say reasonable time for the test generation, I mean few weeks. Reasonable time for test application is few seconds, and reasonable time for to generate the test is few weeks. So within few weeks I want to generate the test vector, and perhaps it may not be possible to generate the test vectors in few weeks. Then what to do? Of course, mostly here combinational test generation is fine. We can generate the combinational test pattern using combinational ATPG, even if I have billion gates. So what is my sequential circuit? I have this state register, provide input here. This is my combinational logic, output, and then the primary output, right? And I'm testing the faults which can occur somewhere inside this circuit, right? Now if I generate this fault, in that case perhaps it may demand some value from here, right? Value 1 from here and value 2 from this one. And when I propagate the output, it may go to the primary output, or it may go to the pseudo primary output, and producing value 3 that will be stored in this register. Now is there any possibility to just get away from the sequentiality of the circuit if I can look at this structure? Though from the external point of view I have external interface as primary input and primary output, but if I want to consider this circuit as combinational logic, and I can carve out this, and if I can make sure, if I generate the test vector from this one, assuming that all my the pseudo primary inputs are primary inputs and pseudo primary outputs are the primary output, in that case I can use simple combinational test generator to generate the test vector. That's easy task, relatively easy task I should say. It's not easy, but it's not easy. That's why the companies are spending a whole lot of money on testing. So what I need, I want that my say test generator should be able to so I can use only combinational ATPG. ATPG is automatic test pattern generator. So I can use only if I can say, if we make sure that we can assign any value in state register and read the value of state register at any time. If I can make sure that here this value I can read at any point in time and this value I can assign at any point in time, in that case I can consider these as primary inputs, pseudo primary input as a primary input and pseudo primary output or primary output. Keep in mind that now in a circuit you may have only say 100 primary inputs, but there may be a say 10,000 pseudo primary inputs and 10,000 pseudo primary outputs. So I will have 10,000 primary inputs in that particular circuit and 10,000 primary outputs in that particular circuit. In a way, because there are multiple primary outputs, and it will find more opportunity to propagate the fault effect to one of the primary output or pseudo primary outputs. And so that means now when I supply the circuit to the combinational ATPG, I simply remove the flip-flops and make them as primary, make the output of flip flops as primary inputs and input to the flip flops as primary output. I will make this or modify this gate level netlist and supply to the ATPG and generate the test vector. So now let's say that here I have this combinational logic, and let's say there are 3 flip flops in this circuit, and 3 flip flops. That means here there are 3 state variables in my circuit, and these are the 3 pseudo primary inputs I am getting: primary inputs and primary output, and assume that there is a fault over here. Now, how I should treat this circuit? I say that here, consider this as primary input and this as primary output from the combinational ATPG point of view. But at the end, I may need to assign value to these state variables. This state variable may be S0, S1, S2, and I should be able to read this. How can I do that? All of us are digital design engineers. We can achieve this by putting a multiplexer here and providing one extra input and one control input for this multiplexer. For another one, I can have another uh, input. So this may be, say, variable V1, this is variable V2, and the third input. So now, and these are the 3 control signals to this multiplexers V3. So if I can have these 3 multiplexers and 6 additional primary inputs, in that case, I can write anything at any point in time in these say flip-flops. So if my combinational ATPG needs 0 from here, 1 from here, and 0 from here, in that case, always I can assign 0 here, I can assign 1 here, 0 here by assigning 0, 1, 0 here. This needs 6 additional primary inputs. That I can reduce by, because I can load all these at the same time. So therefore, I can reduce this number to only 1. I can tie up all these. So I say this as a test enable. TE is a test enable. When I'm testing, in that case, I can put this test enable equal to 1, and then I can load all these simultaneously. So now it needs 4 different primary inputs. But this won't solve the problem, because my fault effect can also propagate to the primary output, and then I have to read it from the output. So this one also I have to read. This I say V1 prime, V2 prime, V3 prime. So that means I need 3 additional primary input. No, 4 additional primary input and 3 additional primary output. Okay, I mean, this may not be very bad if we have only 3 flip-flops. But in practical circuit today, we have a million flip-flops, or rather several million flip-flops. Now that needs 1 million primary input and 1 million primary output, which is unthinkable. Right? So I mean, I add one additional multiplexer with every flip-flop, but now this comes with a problem that I need to have n number of two n number of say additional primary input outputs. That is almost impossible for any size circuit. Now, can you do something better? And idea is yes, you can. I don't need to load everything in parallel. What you can do is you can connect them like this serially. Now, if now what I need one primary input and one primary output. I can load anything, whatever I want to load here in serial fashion. This becomes a shift register. Serial input output. Now from one end we say and that means like here we are scanning a pattern or inside the flip-flops or storage element, and therefore we call this as scan input, and this we call as scan output. So I need only one primary input to scan in, one primary output to scan out, and one additional input of, as a test enable that can put these multiplexers into the test mode. So if there are n flip-flops, in that case, it will take n cycles to load this or unload this. N cycles to load, n cycle to unload. So now it will take longer time, but demands only 3 pins, 3 additional pins. Out of these 3 additional pins, one additional pin is essential, 2 pins. Even this scan in and scan out, you can multiplex with any other primary input and primary output. So in real sense, I need one additional pin. But this will elongate my time required. If I have million say flip-flops, in that case it will take 1 million cycle to initialize this circuit in particular state. And after initialization, I have to apply one test vector in one cycle, and then have to unload the output that I'm getting. Again, it will take 1 million cycle. So then total, to apply one particular test vector, it will take 2,000,001 cycle rather than having one cycle. So my test time will increase, but I don't need any say sequential ATPG or sequential test generator. This kind of augmentation of the circuit for the purpose of making testability better, we call as design for test. DFT, not a discrete Fourier transform. It's design for test, which is which was proposed first time by a Japanese researcher in I think 1962 or something around that time. But the article was published only in the Japanese journal, and it was not known to the rest of the community until early 70s. 70s, like here the IBM invented this, um, or reinvented, whatever you say, the scan based, augmentation and test methodology for a circuit, and 70s onward it became very popular. So some people, say, give the credit to the IBM. Some people give the credit to the Japanese researchers who have developed this algorithm first time. Now this is scan design. This is like a circuit, is, I mean, has to be designed using the pre-specified rules, and I will tell you that what those rules are. This is a test structure that is added to a verified design that I have. So what I need to do here, you can see that with every flip flop I need to add one particular, say this is my flip flop, and with the flip flop, every flip flop I need to have one D input and one is scan input, and this will go as test enable, and this is the clock, and this is Q. So now a flip-flop is augmented with two additional input. One is scan in, and one is test in, test enable, sorry, and one multiplexer. And we call that as a scan flip-flop. So every flip-flop can be, so this become much easier. Every flip-flop can be replaced by a scan flop. Perhaps I believe Professor C.P. Ravi Kumar has discussed this thing in detail, maybe in yesterday's talk. So I need I mean, this hardware augmentation need a test control or test enable, whatever you call, a primary input. It replace all the flip flop by this scan flip flop and connect them in a shift register form, make input output of each, I mean, scan shift register controllable or observable from the primary input and primary output. So one, so additional two primary input is scan in and scan out, that can be shared with the existing primary input and primary output by having additional multiplexers. Then, but the beauty of this is you can use combinational ATPG to generate the test for all the testable faults in the combinational logic. This may result into the over testing of the circuit, because this will generate the test vector for all combinationally testable faults. Some of the combinationally testable faults are sequentially redundant fault, and therefore if those faults are even there in the circuit, they may not result into malfunctioning of the circuit. However, I don't know, we are not looking at the sequentiality. So if I have that fault in the circuit, you will identify that circuit as a bad circuit, but circuit may not be the bad circuit, and you have to throw that out, and then it will result into yield loss. This add shift register test, and so now the question here is, I can test this combinational logic, but what about these, say, flip flops, storage elements? These are the storage elements, like a memory element. So, so shouldn't we need to test it? I need to test it, and you can easily test it by say marching a sequence of 001100110011. It will give you that here, I it can retain the value 0, and it can retain value 1, or it can transit from 0 to 1, or can transit from 1 to 0. All possibilities. That, because there is no address decoder here, so I really don't need to worry about the address decoder fault, but I just need to check the faults in an array, and in array here this particular test set is good enough, that generally we called as flush test. because you are flushing this pattern all through the say your scan chain. And now the how many cycles it will take if there are n number of flip flop, in that case it will take n plus 4 number of cycles, because this 0011 has to march all through the all the flip flops. So so that means here if it is marching through n number of flip flops in the and these are the four vectors, and therefore it will take n plus 4 cycles. So I mean, add the shift register test, that is the like here 000011 sequence, and convert ATPG test into the scan sequence for use of manufacturing test. So now you can see that my flip flop is augmented as like, so we are and I'm now I will explain. As I said yesterday, that we are using D type flip flop. We in master slave configuration, this is the master, this is slave, and we add a multiplexer along with this. Every flip flop is augmented by this. Now you can see how I mean, maybe LSSD I can skip this. The way you can say uh, connect these all the storage element, and there is a test clock or test enable, and then there is a scan in and the scan out of the circuit. When I am applying the test vector, in that case, first you have to load the test vector, apply the test in one cycle, and then unload the test vectors from the response from the flip flops. So now here in first, it will load the first test vector, apply. So now maybe I can say here. So say if I have some primary inputs, let's say m primary inputs and some primary outputs, and these pseudo primary inputs. Pseudo primary inputs are n number of flip flops. Then first I have to load all these. It will take for the test application of test vector, it will take n number of cycles to load all these. Then in one cycle, I have to apply at the primary input all the m inputs parallelly, because I have all the available all primary inputs are available, and at the end I have to transfer the test response to the primary output, and therefore we have to scan that out. So every test vector will take 2n plus 1 cycle. However, now here is, so let's say that here if I have m number of test vector, in that case I may need this many number of cycles. However, because this is a shift register, when I am scanning out this one, I can scan in the next test vector. And therefore the next test vector will take n cycle to load, one cycle to apply the test, and one cycle to unload it. And these two can be done in parallel, because one bit is going out and another bit is coming in. These things can happen simultaneously in n cycles. Now V3 will take n cycle to load, one cycle, and then n cycle to the output, and this can be say at the same time concurrently. And you can find out that how much time it will take. This will take n plus 1 into m plus n number of cycles. Right? So that means here if n is, let's say, 1 million, and my say if I have test vector m is 10,000, it will take 10 billion cycles. You can see there is a increase in the test time. That give more say pressure on the number of test vectors that you are generating. So that means your test set should be as compact as possible. So I have to apply the load the test vector, apply in one cycle, and unload the test response, and at the same time you can load the another one. This I already explained you. Uh, so now see, with every flip flop, you can see here maybe a rough calculation if I do, then every flip flop that has how many 10 gates, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 gates. Along with the 10 gate here, I am adding 4 more gates. This is the additional overhead. Additional overhead, if you count, in that case, now this will become, say, here 4 flip flops. So that means your total number of additional gate I need 4 into the number of flip flops that I have. This is divided by the total ng is the number of combinational gates that I have in the circuit, plus this 10 flip flops I had already. Say 10 gates per flip flop I had already. So that means 4n divided by ng plus 10n into 100%. This is the overhead. If you take some ballpark figure of the number of gates and say number of flip flops, in that case, it comes in the order of like a 5 to 10%. So I need to augment my circuit by 10%, just to make sure that I can use the combinational test generator to generate the test, and I can test that particular chip. I remember some people like Professor Ingwa Min in China. He used to say that we people in the sequential test generator community did not do that well. That's why till date these scan chains are surviving with humongous overhead. This needs additional area. This needs additional say primary inputs, as well as it needs a, because in every combinational path one additional multiplexer is coming in the picture, and delay is extended by a delay of a multiplexer. That became very big issue maybe about 10, 12 years ago, or about say 10 15 years ago or so, when we were going for relentless technology and a relentless frequency increase, and at a time there were only 5 6 gates between two flip flops, and then within the 5 10 gate I mean 5 6 gates, if you are adding one additional multiplexer that may come with 2 gates in the path, is too much overhead onto the performance. Now perhaps because we are not increasing the frequency, in that case you can have multi-level logic, and that the multiplexer delay perhaps may not be that significant. So this is how we today today's design, we are using the scan chains to say test. So let's say that here this example of S5378 a circuit, which is a SCA-89 benchmark circuit. This says that here this circuit has about 2,800 gates. Number of flip flops are say 179. In one I use the original circuit, another one I make the scan circuit. If I make it scan circuit, in that case of course there would be augmentation, and then the area overhead that we obtain is about 15% additional area it will incur. Number of combinational faults are same, 4600. And if I do the combinational ATPG, oh sorry, sequential ATPG, it will take about 5500 seconds and can obtain only 70% fault coverage. On the contrary, if I augment it with the scan, in that case we can achieve 100% fault efficiency, and only you can generate the test vector in 5 seconds. You can see that here about 3 order of magnitude difference, 5 seconds and 5000 seconds. However, the sequence length will become longer, about 1 lakhs. So it will take 1 lakh cycles. If you are using sequential ATPG, in that case, number of vector sequence or vectors would be 414. So it will take about 400 cycles. Is much more compact. Now, when I use the scan chain, in that case, it comes with the some rules, and rules are as follows. Maybe may I take 5 more minutes?
Yes, sir. There is one
So
question also, sir. There is one question
yeah,
also
yeah,
to
yeah,
check
yeah.
box.
So
He's asking 5 second is to generate the test vector or to apply the test vectors. In the previous slide, probably you mentioned 5,000 times and 5,000 seconds and 5 seconds. So he's asking about that. Yes, sir.
so if I use a sequential, no, the combinational ATPG, it takes 5 seconds, because I will take the combinational part, convert all the flip flops into the primary input and primary output, and then give it to the combinational ATPG. It will take only 5 seconds. If I do the time frame expansion of the circuit and generate the test vector, in that case it is able to generate the test for 70% of the faults, and that is within 5000 seconds. Very large time, 1000 times more time it will take to generate the test vectors. But
So,
the
sir,
test,
I just want to ask whether it is not same time frame expansion. We used to remove the flip flop and then we have to take the combination
no,
part.
no, 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 no. It's only the combination logic. So it takes only if it has 1000 gate. In that case, it will generate for the 1000 gates. If I
Okay.
do the time frame expansions, let's say that 10 time frames, then the 1000 gate will become 10,000 gates.
Okay.
So that would be much larger circuit. And now if it is a sequential, I mean cyclic circuit, in that case, you don't know how many number of times you may need to unroll that circuit.
Correct, sir.
And therefore there are whole lot of aborted faults. Only 70% fault efficiency you obtain. That means for 30% times you have just aborted. You don't know whether there exists a test vector for those faults or there is no test vector. I can only say confidently with 70%. Now, if I say, if I relax the say my abort time, in that case my time to generate the test vector will increase tremendously, and still means getting the 100% fault efficiency is almost impossible if you are using sequential ATPG.
Yes, sir. Thank you, sir.
So so now when we are doing this comes with certain rules that we have to follow, because now I use this circuit here I made. Every flip flop will have, say, this one input as a scan input, and I'm putting this say a multiplexer in front of that particular flip flop. Now, first of all, because whatever value I want to add, I have to, and keep in mind that if I have n number of flip flop, in that case my time would be test time would be expanded, or would be simply multiplied by that factor n. Now if I have a storage element that has one input and one output, and that is expected from any storage element, maybe we can discuss sometime separately that here why somebody thought to have the storage element with multiple inputs like SR, JK kind of flip flops. There's no reason to have something storage element wherein you have two or multiple inputs. I need to have one input and one output, and whenever clock pulse comes, in that case here it should be able to load that value. That is anything one can easily think of. But if I have one input and one output, in that case I need one multiplexer, and then with that multiplexer you can load this value as I mean whenever the clock pulse comes. And so then my test time would be n times, and it is much easier. Whatever value I want to load into this, I can propagate that value. If I use another kind of flip flop like a SR or JK, first of all it has two inputs, and I need to know that here to have store zero, what value of S and R or J and K I need to have. So that computation will again take some time, and then the length will become twice. I need to have two multiplexers rather than one multiplexer. And in place of having my test time increase by n times, now it will increase by 2n times. So say that here my test time increase 10,000 times or 20,000 times. That will have impact on the cost, because cost will become double, because now more or less the test time is dominated by the time during which you load the flip flops and unload the flip flops. And if this time become double, in that case my total test cost will become double. You don't want to have that. As I said, per second I am paying 5-6 rupees. Any increase in a second, maybe you may need to pay 5 or 6 more rupees. So therefore, first thing is very important is you have to use flip flop which has only one input and one output. And therefore we use only clocked D type flip flop. In using two D type latches in master slave form, and these are much more, say, much easier to implement. What is a flip flop? Flip flop is just like a back to back connected inverter. No, sorry. Yeah, flip flop is or store element is back to back connected inverter. Now, in order to write into this one, what I am doing here is you just have a switch. When you want to write, you open it, and when you want to say retain, in that case you can close these switches. Much cheaper to implement than any other flip flop we can use. So only and only D type flip flop is needed for all state variable. At least one primary input must be available in your chip to provide the test enable pin. Test enable or test control. Test control or scan enable. Different literature used a different name for that. All clocks, another thing is all clocks of all the flip flop must be controlled. बरनाबास जी, बरनाबास जी, बंद करेंगे क्या इसको एक बार? All clock must be controlled from the primary inputs. That means no clock should be gated one. All clocks should be controlled by the primary input. So that means there is a clock input in the circuit, and that directly that clock input should go to each and every flip flop. That should not go through any logic. Clock must not, so yeah, clock must not feed data input from the flip flop. Now, here what it means that here, so all clock must be controlled from the primary input. So you have primary input, but I cannot get this, say, many times when you are designing, it is very easy. You say that here, oh, I want to implement a, say, counter, and in counter you can say that, okay, the clock of the next flip flop I can give from the output of the current flip flop. That is prohibited. Like for example, in this design style, there is a primary input D1, and based on D2, you can say if D2 is equal to 1, in that case it will provide the clock, and then it can flip the value. Otherwise it will remain the clock 0, and then nothing will happen. So that means here, if D2 is equal to 0, in that case no action happens over here. Now this particular circuit is a gated circuit. That is prohibited. There should be clean clock supplied to every flip flop. Therefore, if you want to do this kind of thing, in that case, you have to make or modify your circuit and bring in this, say, D2 in your logic that goes to the input of the flip flop, D input of the flip flop. Alternatively, I can implement the same thing using the larger logic. Of course, in the amount of logic will increase. So in order to optimize, you can prefer to go for this, but then it will, say, uh, uh, it will make the circuit to test difficult. Why it will make circuit testing of the circuit difficult? Because in order to generate the test in the combinational logic, in case, let's say that here I need 0. So if D2 is 0 is needed to excite any particular fault, in that case what will happen? That as a fallout effect of that, if I assign D2 equal to 0, it will suppress the clock, and the output, I am expecting that here the output of that particular fault effect would be loaded into this flip flop, but then that won't be loaded into this flip flop, and I may falsely consider that my circuit is good even if my circuit is bad, and therefore this is not allowed. These are some of the guidelines that one has to follow when you are making your circuit as a scan circuit. This, like here, making circuit as a scan circuit became very standard exercise in the industry right from 70s. It is still going on. Many times people say that here scan is there to test the circuit, and I need that only once when I'm testing after the manufacturing. But when I have this scan infrastructure on the circuit, this provide me some additional benefit, that is for the debug, that anytime I can scan in, I can stop my chip and then can take out all content of all the flip flops at the primary output. That helps me in debugging my system, that here what went wrong if something goes wrong. So this scan design provide me additional support for debugging. So it's not only now being used for testing, but this is also used for the debugging. And ZTag is one such say interface in which we can use this scan chain to scan out the all the contents of the flip flops, and then you can debug this in much more easier way. Become bit say better for debug. So with this, I close this discussion today. If you have any other questions, please feel free to ask. Oh, somebody said that the 5 second is to generate the test vector or apply. No, 5 second is to generate the test vector, not apply the test vector. Apply test vector would be you can compute how much time it will take. Sequential circuit will say combinational circuit will take 105,000 cycles. So that means 1 lakh cycles. And if circuit operates at say 1 gigahertz, you can compute how much time it will take. And in as opposed to that, if I apply if I use sequential test generator, in that case it needs only 414 cycles. Can compute that how much time it will take. 414, if I operate at circuit at 1 gigahertz, in that case it will take few microsecond, half a microsecond. Whereas this will say full scan circuit may take close to a millisecond, about 10 milliseconds. So that's the difference. The test application time is almost like, here you can say 100 times, no, 1,000 times. It will be 1,000 times, because there are no about 200, 179 flip flops. So the time would expand in that proportion. Uh, One more. Oh, I will share the material. Yes. Any other question?
Dear participants, if you have any questions, please
Okay,
type
okay.
in the chat box. Otherwise, we are going to this topic. So thank you so much for your valuable time, sir. Your all lectures were very insightful, sir. Definitely, I believe all the participants will get benefited out of that, sir.
Thank you very much. This is the last lecture, so I thank all of you, and then MNIT and Savla sir for inviting me to have this discussion with you people. I hope this will benefit you in offering the course, and say for the students, helping in getting insight into the test issues. Generally, the test is very much ignored subject in during the undergraduate study. People think that what is there in the test, it is a circuit, I apply input and then check the output, and now it is easy. Of course it is easy, very easy exercise. Nothing can be as easy as the testing of a circuit. If I have a small number of inputs, 5, 6, 10, I have tested during my undergraduate study many small circuits by simply applying all possible inputs.
True, sir.
But i-
I
if
Yes, sir. So I think you made it really very easy to how to check the sequential circuits, and you told the correct difference between the combination and sequential ATPG from the industry and whatever the current research is going on to test the sequential circuits. That is actually, I think, the added-on advantage for all the students and faculty members. So thank you so much, sir. It was really enlightening talk. All of your talks were very insightful, and it was including the industrial perspective and the research perspective also. Thank you so much, sir.
thank you, ma'am. Thanks a lot.
Thank you, sir. So, dear Gaurav, hello.
Yes, ma'am.
We will be starting the next session at 11:40. So, may I request you to switch the session, please?
Sure, ma'am.
Okay. So, dear participants, we are going to start our next session at 11:40.